Hello, everyone. Dear friends, dear colleagues, I'm so glad to welcome all of you today on our webinar dedicated to the MOLUSCE. Today we would have hands-on land cover change simulations in QGIS with MOLUSCE webinar. My name is Edward Kazakov. I'm from NextGIS, and I will be your guide today. What we would have today would be a mix of theory and practice. My purpose here is to prepare you to MOLUSCE usage, to make you understand what it can do and what it can't do. During the webinar, please feel free to share your questions, ideas, skepticism, etc. in the chat. And after I finish, we will be able to talk using microphones and cameras. I would be very happy to see and hear all of you. But during the webinar itself, I kindly ask you to mute your microphones just for us to have some smooth process. Everything is fine with audio and image. We're good. We're good to go.
Yes, it's very clear.
Very nice. Very good. Okay, so let's start. All the materials, including this presentation, are available for all of you here. Please use this link. You might find it in the Zoom comments as well. Yes, Dmitry highlighted it in the comment as workshop data. Feel free to use everything, reuse, organize your own workshops based on this one, use the data, use the presentation. Everything is for you. So please don't hesitate to do it. To start, a couple of words about ourselves. We are NextGIS, geospatial software developers since 2011. Now based in Estonia and Serbia in Europe. And we are product developers having our own set of software, and we are largely open sourced company. Almost everything we do is open sourced. I believe that you have been using our software for quite a while, because we are core committers in projects like QGIS and GDAL. We are the largest public QGIS plugins developer in the world, the most used plugin ever, Quick Map Services with more than 10 million downloads, is our invention, as well as today's hero, MOLUSCE. And we are also long-term supporters of OpenStreetMap. We develop a lot of things, the geospatial software ecosystem, but one thing I want to highlight now is our solution to build QGIS team spaces, allowing you to seamlessly collaborate on QGIS projects with a lot of enterprise-grade features like built-in web maps, role-based model, data version control with possibility to roll back changes, conflict resolution system, and more. And it is all open sourced, so if you are interested, please visit our website, nextgis.com, and contact us. I know there are a lot of people from academia, because MOLUSCE is very interesting for people from academia, from universities, and for you we have a very good special program with cloud access to our platform at zero cost and 50% discount on everything else. So if you are interested, reach out to me directly or email to edu@nextgis.com. You can find more information on this program at our website. Very well, go back to our today's topic, the land use change simulation problem. Usually we have two types of questions regarding land use dynamics. What and how had changed in the past, and what will happen in the future based on what we observed. So we usually have two questions: what and how had changed, and what will happen in next 3, 5, 10, 20, etc. years. So we will try to answer these questions today. MOLUSCE is a tool for answering both these questions. It was first released in 2012 by NextGIS in cooperation with Asia Air Survey, and after version 3 release in 2018, 2013, development was put on hold for a long 11 years. When we returned back to the support and released several updates, including QGIS 4 support and several major functionality improvements. So we took a control back, and it's very good news for us and for all MOLUSCE users. We try to maintain an adequate level of manuals available, and I record a video on each release. These videos are published on YouTube, NextGIS channel, and we also keep PDF manual updated, which is available in MOLUSCE distribution. So there are a lot of information you can use to learn MOLUSCE and find some use cases, etc. During these years, MOLUSCE became a real phenomenon in the QGIS world. With more than 100,000 downloads, it is cited in thousands of peer-reviewed scientific papers, including top-level research. You can also find a lot of YouTube videos by users sharing their experience and case studies. So MOLUSCE has proved its value for the community, and we are really proud of it and proud to communicate it to you today. Very well. Let's move forward to see how MOLUSCE works. MOLUSCE is based on two well-known principles united: Monte Carlo and cellular automata. Imagine we have some state of land cover represented in raster form as a matrix with values reflecting different types of land use. For example, 2 for trees, 7 for built-up areas, 11 for grasslands, etc. Let's say this is a state for year 2020. We have a second state. Let's say the year 2025. Time passed by, things have changed, and now we have this configuration, changed land cover. No more trees, more built-up areas. So we have observed some kind of land cover dynamics from this to this state. The first thing we want to do with it is to define what has actually changed and how. We built a transition matrix showing how different land cover classes have changed. For example, this table shows that 28% of crops turned to built-up areas. We also built a class statistics table showing what changed in each class. MOLUSCE creates both very simply, and we will do it today. Then we want to predict the future state of our land cover. In order to do that, we have to build a model and propose environmental factors affecting the transition. For example, it could be annual temperature matrix, elevation slopes matrix, distance to nearest settlement matrix, etc. Anything we consider as the reason our transition happened. So the very important step is to formulate hypotheses, to formulate set of environmental variables affecting the transition we observed. We can collect many such factors, 2, 3, 5, 10, 20, 100, as many as you can propose. So we building a hypothesis knowing our territory, knowing what drive the change. And there could be dozens of factors taken into account. It's on you as a researcher to propose these environmental factors. Cellular automata principles allow us to take into account also neighbor cell state. So our model relies on both environmental factors we provided and special configuration of land cover. Then we take all this information, observed changes, all environmental factors we proposed, special configuration of land cover classes, their relations with neighbors, and pulled all of this into statistical model. MOLUSCE supports 4 statistical models: artificial neural networks, logistic regression, weights of evidence, and multi-criteria evaluation. Selected statistical model takes all the information we have and trains to predict the next state of land cover. As a result, we got probability estimation for each transition. For example, this is a map of class 11 to class 7 transition. We can see cells where this transition is very probable, like 88%, 77%, and where it is very improbable, for example, 2%, 3%. We got such maps for each transition pair, including no transition scenario. For example, where class 11 remains class 11. MOLUSCE also calculates general certainty function as a difference between two largest transition potentials. For example, if we have in pixel 2 transitions with 50% probability, model is very uncertain, 0% of certainty. Such map would help us to understand the places where a situation is uncertain, and we will work with such confidence rasters today. And finally, highest probability is used to apply the transition. If there are several very close probabilities, random among them is selected. Very well. Finally, we get a predicted state. The prediction step is equal to the step between two initial land cover datasets. We had 2020 and 2025 here. Yes, 2020, 2025. That means that step is 5 years. So prediction would be made for 2030. There could be many iterations with this step. For example, if we set 2 iterations, we get a prediction for 2035. We can set 10 iterations and get like 50 years prediction. MOLUSCE is very popular and it has been used in thousands of studies. Most of them are dedicated to general land cover dynamics for different regions across the globe. So putting QGIS MOLUSCE in Google Scholar or Scopus search or Web of Science search, you'll find thousands of case studies, which could be helpful for you to understand what environmental factors do people use in different cases and how they handle like challenges, etc., etc. Some bright example of such work is presented on this slide. MOLUSCE is also used in papers researching some particular processes, like, for example, deforestation, desertification, or urbanization. Another nice example is like long-term, very long-term predictions up to 2060. And for example, for predicting shoreline dynamics, especially for freshwater bodies. So you are not limited to like general land use land cover dynamics. You can apply it to any spatial dynamics, which could be reflected in like categorical maps as forest, not forest, water, not water, productive land, not productive land, etc. Okay, let's move forward and practice. Our training case for today is Ramsko Lake or Ramsko Jezero, located in Bosnia and Herzegovina. A really beautiful place. I love it. This case is a little bit trappy, and I chose it for a reason to show how careful you should be when modeling land cover change. Our purpose is to train a model based on land cover data for 2018 and 2021, then make prediction for 2024, validate it using the real data for 2024, which we have, and then make another prediction to 2027, for example. I will use as a real land cover dataset and several sources of data for special variables. Digital elevation model from Copernicus, touristic points from OpenStreetMap, and 2 datasets based on neural networks, Microsoft Buildings and Microsoft Roads. All these datasets are public domain. Links are mentioned here in this presentation, so you would be able to play with it as well. Okay, let's open QGIS and take a look at this project with raw data. I have it somewhere. Give me a second. Here it is. In this link, Dmitry shared for you in Zoom chat, you'll find the same project, so you would be able to repeat all these steps we're going to perform today. What I have here. So I have land use, land cover datasets for years I mentioned here in, well, land use, land cover folder, 2018, 2021, 2024. I have an area of interest polygon, this red rectangle. It's approximately 2 kilometers from the Ramsco Lake border. We also have this Ramsco Lake as a vector layer. And I have 4 factor datasets. I have, let me enable them one by one. I have touristic points. I have highway lines. I have buildings and digital elevation model. That's what we have. All the data is from pre-public sources, again, so you can try to reproduce the steps anywhere in the world, downloading the same datasets on your territory of interest. Please remember that this case is a training one, and I don't try to build real scientific simulation, just show the principles of how it all works. Now I'm going to install Mollusc. I go to plugins, manage and install plugins, go to all and search for Mollusc. Here it is, NextGIS Mollusc. I push the install button. After installation, Mollusc appeared in 2 places. In raster menu, here, and also I got something in the processing toolbox. You can see NextGIS Mollusc block in the processing toolbox. Processing toolbox in QGIS is the main place where you can find data processing tools like buffer zones and all this stuff. You can open processing toolbox using this menu, processing toolbox. And now we can find NextGIS Mollusc block here with several helpful tools. We will use them today. To run the Mollusc workflow, the very important step is data preparation. So let's talk about what Mollusc wants for inputs. And first we will discuss it theoretically, and then we'll try to implement the data preparation step on practice. In general, Mollusc wants to have everything, including land cover datasets and all the special variables you want to use, as rasters, having the same size, extent, and special reference system. For example, if you have the first land cover map as a raster with size 2400 by 2400, everything else you plan to use should be also presented as rasters with size 2400 by 2400 and in the same special extent. So your task is to turn everything you have into such unified rasters. If you have raster dataset as special variable, you could just resample it using raster calculator, GDAL warp util, and other standard QGIS tools. And I will mention it later. We now have very handy, ready-to-use processing tool built into Mollusc. If you have a vector dataset, there could be different ways. For example, you have points as predictors, as we have touristic points of interest in our training case. First thing you can do is to turn them to raster by using rasterization tool. So you'll have a raster with all zeros and non-zero values in point location. I call such rasters presence rasters. We simply use information about whether we have a point in the pixel or not. Usually it's quite a useless approach for Mollusc, and simplest way to improve it is to rasterize not points themselves, but buffer zones around them. So we create some kind of influence zones for each pixel. As we will have, for example, 100 meters buffered zone rasterized as our predictor. Does point influence this area or not? If these points we have represent measurements, not just presence of some phenomenon, for example, temperature or I don't know, concentration of some matter in the soil, etc. you can turn them to raster using one of the various interpolation techniques. For example, you can use triangulation or inverse distance weighting algorithms built in QGIS, or use a lot of algorithms. For example, Saga provides integrated into QGIS. It's a relatively rare case when someone use interpolation to prepare the data, but still, for some cases, it is like right way to act. And the most popular way to prepare points is to calculate proximity raster. A raster where each pixel stores the distance to the nearest point. It is very, very widely used approach in MOLUSCE. Like a lot of case studies focus on proximity as the main predictor. And we will try to work with proximities today as well. For linear and polygon layers, the preparation process is similar. We can rasterize objects with or without a buffer, and we can calculate proximity rasters. Distance to roads, distance to buildings, distance to coastline, etc. In some rare cases, you can come up with some other like concept of preparing the data for MOLUSCE, but this presence and interpolation and proximity approaches dominate. So yes, data preparation has always been a very long process. So on some workshops, I spent several hours for people to like prepare the data. So we finally delivered easy to use processing tools. I will show you them in action. These processing tools are available in QGIS processing toolbox. So you can see on the screenshot that we can, in one click, generate proximity rasters, presence rasters based on like some extent and special domain of reference raster we can choose. Okay, go back to QGIS and let's try to work with it in practice. The first step is to manually prepare the most important reference land cover dataset, to which we would transform all other datasets we have. I will use Esri 2018, this raster. Hide all layers, turn it on. I will use this land cover dataset, and the only thing I'm gonna do is to crop it to the area of interest. Here is my area of interest, and I will run standard clip raster by mask layer tool from QGIS processing toolbox. Select this Esri 2018 as input layer, select area of interest as mask layer, and what else should I do? I should assign 0 as no data value and activate the flag keep resolution of input raster. It would help us to minimize land cover data distortion, which is very important because land cover data is like the main thing we have in our project. And I will save the result to the file. Let me create a new folder. I will call it process, and I will call my raster Esri 2018 prepared. Let's check. Everything is fine. Let's run. Okay, I got new prepared raster cropped to the area of interest. And now I have a reference raster. Next steps I can perform using MOLUSCE processing tools. Let me find them here in processing toolbox, NextGIS MOLUSCE log. I run prepare raster dataset for MOLUSCE tool. I select raster to be prepared. Second land cover raster Esri 2021. I select reference raster. It's our prepared Esri 2018 prepared. When resampling categorical rasters, it is very important to select nearest neighbor resampling algorithm to prevent appearance of new data classes as a result of interpolation. We can talk about it more if you want about resampling algorithm, etc. But the general simple rule is to use nearest neighbor if you resample categorical rasters, and to use linear or cubic algorithms when you resample continuous rasters, as for example digital elevation model or temperature or something like that. I save the result to Esri 21 prepared, run the tool, and I immediately got perfectly shaped land cover raster resampled to the special domain of our reference raster. I repeat the same procedure for Esri 2024, simply switching the number. Okay, great. We have all three land cover rasters prepared and ready to be used. Yes, a thing to care about here is style, I guess. You can see that in original rasters, I have nicely designed style as paletted unique values with labels and properly set colors. And after resampling, for some reason, QGIS loses this information. So I simply take style from original raster and paste it to all prepared rasters. So now they also have these labels and proper colors. It would help us to work with MOLUSCE as well. Let's proceed through vector layers. First, I will take OSM tourism point layer. I'll close this one, disable this layer, and enable OSM tourism point layer. I want to get proximity raster shaped in this red rectangle, containing distance to nearest touristic point in each pixel. So I run prepare vector dataset for MOLUSCE, select OSM tourism as input layer, select Esri 2028 prepared as reference raster layer, and then I can choose how do I want to prepare my points. Two modes we have discussed are available, presence and proximity. I choose proximity and save the result to a new file, for example, tourism proximity. Tourism proximity. I run the processing. It has done everything. And we got ready to use proximity raster adjusted to our land cover datasets. Each pixels, I will examine them with identification tool. Each pixel contains the distance to the nearest touristic point. For better view, we can see that, yes, I click nearby existing touristic point, I have a small distance. I click somewhere far away and I have big distance. Very well. So I simply repeat the same procedure for buildings. And roads. Very well. We have now three maps ready to be used as environmental factors for MOLUSCE. Roads proximity, buildings proximity, and touristic points proximity. Now I take the prepare raster dataset tool again and select digital elevation model as input, DIM. I select Esri 2018 prepared as reference raster again, and I choose cubic resampling algorithm, which is much more appropriate to interpolate digital elevation models. If you will resample digital elevation models using default nearest neighbor algorithm, you will probably break your digital elevation model and make it unusable for post-processing. I save it to the DEM prepared file, and run processing. This is our digital elevation model, also resampled and properly prepared for MOLUSCE workflow. The only thing here is that elevation itself is usually not a very good choice in terms of predicting factors. If we don't work with some large mountain areas where elevation zoning plays its role, yes, and you have thousands of meters difference between different pixels, etc. In cases like this one, it is usually better to use some kind of derivative, for example, slope angle. So let me quickly calculate the slope. I find it in processing toolbox, select dim prepared as elevation layer, and save result to example slope prepared file. What we got is this pretty slope angles raster dataset. Again, perfectly shaped and having the same special domain as our all other rasters. If I zoom in and compare different rasters, you will see, give me a second, rasters, toolbars, raster toolbar. Yep. If I will compare these rasters, I will see that they are pixel-wise. So each pixel in one raster has perfectly the same placed pixel in all other rasters. That was our purpose in terms of data preparation. Before we go, short block regarding land use land cover datasets and their sources. I think that's it's like relevant information here. There are several global public domain datasets, and using them, you can build an experiment like ours current very quickly. The most trusted datasets are MODIS MCD12Q, Esri cover we use today, ESA cover, World Cover, Dynamic World, GLC VCS 30D, and GLAT. So you can Google all of them and freely access them in any corner of the earth. So that's why they are very popular and useful. But of course, global datasets have their issues. They have noise, they have mistakes. They usually don't know your like local specifics, etc. So they are good for like large scale, planetary scale research, but they are not always good for like local specific research. And to support like more local research, or if you want to dig deeper into history, another important source of land cover data is topographic and thematic maps for your territory of interest. Usually topographic maps are much more accurate than global data sets, but you need to find such materials, and then after you find them, they require a lot of effort to prepare and to digitize, to interpret, etc. To prepare a land cover dataset, it could be quite long and tricky step. You can also use satellite and aerial imagery to process it yourself and generate land cover maps. There are a lot of interesting aerial imagery from the middle of the 20th century, which is very useful in like rebuilding historical landscape, etc. And now we have a lot of like modern satellite imagery in public domain. So of course you can use this to produce your own land cover maps assigned to like very particular periods of time. In some countries, there are also national cadastre services good enough to provide you with such information. Usually this information is open, but depending on the country, the quality could be very different. And in real cases, you would most likely be forced to combine the data from a lot of sources and then unify them. An example I personally like very much is the paper about Norfolk Island land use changes, where authors aggregated and unified a lot of sources starting with the 1794 map. And so they unified all these various data sources using the same legend And such retrospective could be very interesting for studies of land cover change dynamics, and very interesting for to be applied in MOLUSCE in particular. Very well, go back to QGIS and let's run MOLUSCE in the end. That's why we are here. I go to raster, NextGIS MOLUSCE, NextGIS MOLUSCE. And this is what I have, MOLUSCE interface. MOLUSCE interface is built as step-by-step tabs. And now we are the input step, and we can go to the next steps until we do our homework here. We have to select two land cover maps we will use for training. And set of special variables explaining why these changes happened. I select Esri 2018 as initial raster. I press this initial button, and I select, oh, no, I made mistake, Esri 2018 prepared, of course, yes, this one, and Esri 2021 prepared as a final land cover map. Then I select building proximity, roads proximity, slope prepared, and tourism proximity, and add them to special variables list. I push check geometry button. It controls if all the sources I selected have the same special domain. And if it's so, other tabs unblock. If something is wrong with one or more of your inputs you selected, you will have an error message explaining that one of datasets you selected is not like matches the selected land cover datasets. We used built-in MOLUSCE data preparation tools, and they made it easy for us to prepare everything in the right way. Second tab is evaluating correlation. It is optional, but it could help you to better understand special variables you chose. By default, I get Pearson correlations for each pair of variables. Let me check. I can see that buildings proximity and roads proximity have very high correlation, near 0.8. So probably we can exclude one of them from the model because they are very similar. But I want to exclude it for now. All other correlations are more or less low. If you use categorical data as predictors, we now use all continuous predictors, yes, numbers, meters, etc. But if you use categorical special variables, you should use Cramer's coefficient to estimate the correlations. And Pearson's correlation is for continuous data. Next up is area changes. It's super important and could be very helpful even if you don't need to perform any predictions. It could help you to analyze what you already have. This tab analyzes the current land cover change. I use the Update Tables button, and MOLUSCE calculates class statistics and transition matrix. They both could be copied using right mouse button click. So I can copy entire table, paste it in my, I don't know, LibreOffice writer, and then use it, for example, to publish my article. The class statistics table describes what happened with each category, how its area changed during a given period in selected units and percent. I can select, for example, square kilometers here. For example, we lost almost 2 square kilometers of water. We can see it here. The transition matrix table shows exactly how classes transformed to each other. For example, I can see that here, for example, almost 11% of water turned to rangeland. So we observe some significant water loss. And very important note about this table, to have proper land cover class labels and colors here, you can see that it's very pretty looking. I have class labels, I can see colors here. For it to work for you, your land cover dataset should be styled using, let me show you. using a paletted unique values render type. So before proceed to MOLUSCE workflow, it's better to style all your land cover maps in this way. Okay, go back to MOLUSCE. Now I have to create a changes map using this button. I select the path, set up the name, changes, and get a new, very useful raster. It's been automatically added to the QGIS. Here it is. I will drag it up. Yes, here it is. In each pixel, this raster contains information about the actual transition happened in this pixel. You can see it by legend, yes, colors are referenced to some particular transition types, crops to water, built area to water, etc., etc., etc. To use this raster with comfort, I go to the properties, find attribute tables tab, and create new attribute table from current symbology. What is it for? Thanks to this mechanism, now I can click to any pixel with a identification tool and see readable explanation of what happened in this pixel. Now QGIS highlights the pixel, and I also have this very helpful explanation, so I can explore, discover this process with comfort. Great. Go back to the MOLUSCE. We are ready to proceed to the model training step. Next step is transition potential modeling. The first thing we should do is to select a mathematical approach to be used. 4 methods are available. Artificial neural network, the primary method for MOLUSCE. Logistic regression, it's a second popular option, simplified algorithm. Weights of evidence, it's quite rarely used simple model, and multi-criteria evaluation designed to predict a particular transition between two particular classes when we are able to manually determine the importance of environmental variables. I rarely see this weights of evidence and MCE algorithms in action. We'll start with ANN, Artificial Neural Network, and as we can see, there are a lot of parameters to be tuned. And now we will work for them to understand what should be tuned here. I go back to my presentation. First parameter is neighborhood. It determines how many neighbor pixels to use for each case. If I set up 0, no neighbors would be used, just pixel value itself. So if you think that model should consider what is around each pixel, use 1 for this pattern or bigger value. But keep in mind that each step significantly complicates calculations and makes them longer, etc. Learning rate is the step of the learning process, how much to change the model in response to the estimated error. In short, the lower this value, the more cautious your model is. Next parameter is maximum iterations. The limit of learning cycles. You can decrease it to make the process faster and to avoid overfitting in some cases. But too low value could cause model underfitting. We will play with it a little bit. Next parameter is number of hidden layers. It is about the neural network architecture. The more this number is, the more complex the neural network would be, with a larger amount of internal parameters to be optimized. So low value refers to simple neural network. High value refers to complicated neural network. And finally, momentum defines the influence of the previous learning process step on the next learning process step. It's very technical thing. Go back to MOLUSCE interface. I'm going to use 1 pixel neighborhood. Learning rate, let's say the lowest value possible, 0.001. In my experience, learning rate affects the training process very much. I set maximum iterations to 15, not just for time optimization during our workshop. And momentum, like I have this value 0.05, and I think it's quite good. I also leave hidden layers number 10 by default. Another important block here is define samples. You can see it on the top of the interface, define samples. We can't take all the pixels we have by default, because there could be billions of them. If you have big rasters, you have billions of pixels, and it is impossible to take all pixels into account to train our model. So we generate a given number of random pixels. In these pixels, we generate as samples. We'll take transition information, special variables information, and train the model based on it. We can manage number of samples here and the mode. Couple of words about the modes. So the mode all will use all pixels for training process, and it is impossible for large rasters because your computer would say, please no, don't do it. Random used by default is to randomly place given number of points for training. And stratified mode, this mode randomly undersamples major categories, large areas, and oversamples minor categories, small areas, to ensure their presence. Usually people use random or stratified modes or play with them, experimenting with this or this. I will take 5,000 random pixels, 5,000 in the random mode, and finally train the neural network by pushing train neural network button. In the real time, I can observe learning curve and model metrics. Pay attention to current validation kappa. Roughly speaking, it shows the share of situations trained model can explain based on the information we gave it. So the most important metric, like roughly explaining the general quality of your model. And what you have to do is to experiment here a lot, changing hyperparameter values, changing point samples number and point sampling strategy. You should experiment here with all these parameters, looking at the learning curve until you get acceptable validation kappa value. As a threshold between acceptable and not acceptable, I would propose to use 0.8. If you have validation kappa lower than 0.8, the chances that you have proper model are relatively low. This learning curve is informative as well. Let's talk about it a little bit. Ideal case, if you have ideal hypothesis, you proposed ideal special variables, etc., you will see something like this. Smooth improvement at every iteration for both lines, but it's rarely achievable, to be honest. This picture is bad. Chaotic peaks at both lines, no improvements with iterations. Most likely your hypothesis is wrong, and the special variables you proposed can't explain the change. That means that, for example, you propose that distance to roads and, I don't know, NDVI and something like this explains the change, but actual reasons are different, and you have to sort them. You have to think about what can be the reason and change your hypothesis. And such pattern, you can see on the right side, is tells us that we probably have overfitting. It's better to decrease the number of neurons and increase sample count. What I have here is not ideal, but not awful learning curve. We can more or less confidently use such model for further experiments. Okay, so we get some kind of model trained. What I want to do is to save this model to file. It could be useful, and we have the button here, Save Current Model to File. I push it and save my model as ANN1 in mollusc format. Model was successfully saved, and if I need, I would be able to return back to this model later. I will use this possibility to play and show you interfaces for other methods. I switch to logistic regression. It has only two parameters to tune: maximum iterations, the same as ANN had, and neighborhood value. So this model is much simpler. I decrease iterations to 20 just to get some quick result and train the model. It's done. This pseudo R-squared value has a similar function to the kappa. It reflects the model strength. And here we can see sets of the logistic regression coefficients for each transition. You can see here columns have titles referred to particular transitions. So, for example, this column represents logistic regression equation coefficients regarding this transition from class 2 to class 11. I save this model to the file as well. Logistic regression 1 successfully saved, very well. Now I switch to multi-criteria evaluation. Here I have matrix of special variables we set up, and I should specify which transition I want to model. So this multi-criteria evaluation algorithm works with one particular transition from this class to this class. For example, I use transition from class 11 to from class 7 to class 11. In the matrix, I should describe special variables' mutual importance for this particular transition using Sati scale. So go back to presentation. Here I have a table explaining the Sati scale. So Sati scale is just a way to manually determine how one factor is more important than another factor for this particular transition. And the complexity of this method is that you should set all these values manually. So you should understand your territory, your case, and very well, I know that this factor is much more important than this one, etc. You have these numbers reflecting the level of how much this factor is more important than different factor. I go back to this table to show you some simple example. I think that roads and proximity factors are equally important. I can't say that one of them is much more important than another one. So I place one to the matrix cell reflecting these two factors. Slopes are slightly more important than both roads and buildings proximity. So I'll put 3 here and here. And tourism proximity is even more important. So I place 5 here, and tourism proximity is a little bit more important than slope. So I put 2 here. So I got some formulated importance metrics here, and I can push train model data. I got the message that matrix filled correctly, consistency value is low, and the model can be used. It automatically calculated weights to be used, and I can use this model for predictions of these two particular classes transition. I will save this model to file also. if we would like to return back to it later. And last, weights of evidence. This model splits continuous. I have explanations here. This model splits continuous predictor values to categories based on ranges we provide, calculates weights of factors in occurred and non-occurred transitions, and perform a forecast based on weights using very simple equation. Important to say that this approach works only if there is very straightforward connection between factors and their subranges and transitions. So if you know for sure that this distance to roads affects, for example, forest loss very strictly. Usually we don't have such information, but still, for some cases, this method could be useful. I will split all variables to 5 ranges, calculate ranges breaks to classify these factors, and I can train the model. It will take some time, I guess. It's important to say that, as I said, it works only if we have very straightforward connection. In practice, I'm not sure that I faced the case when weights of evidence model helped me. So usually I use artificial neural network and logistic regression for simpler cases. Let us wait until the training process ends. It's important to say that your modus operandi when working with Mollusc is to experiment with your data, experiment with different models. Try this algorithm, try this algorithm, try these hyperparameters, try these hyperparameters. Never like hope that your first choice would be very effective. You have to compare things, you have to experiment. So the main advice I can give you is to experiment a lot to get the most appropriate result. This process has been finished, so now I can save the model to the file as well. It would be weights of evidence, one MOLUSCE model. Okay, so we now have 4 models trained and saved to the files. And I will use the artificial neural network model we train first. For that, I press load model from file and select the saved model. For example, this one, artificial neural network. We could have avoided all the save load procedure if we didn't want to show the training process for all methods. So we can simply train the model we want to use and go ahead without saving or loading anything. My purpose was to show you different interfaces for different methods, explain their parameters, and now we can proceed with the model we trust more. Or we can try different models if you would like. And anyway, this save load mechanism is quite useful for, again, experimentation. Finally, predicting. I switch to the cellular automata simulation tab, and I can generate 3 types of output here. So first type of output is transition potential maps for each pair of transition. I will select some directory. I will create a new folder named transitions. Second thing to be calculated is certainty function. It describes the model confidence for each pixel. I certainly want to get certainty function, so I save it to certainty dataset. And the most important, simulation results, the predicted land cover state. I will name it simulated 2024 ANN 1. Good. All what we have here also is number of simulation iterations. It's very important control. It controls the period of time we want to work with. If I go back to the input step, I see that I use 2018 as initial date and 2021 as final date, which means that the step is 3 years. And if I use the same number of iteration, for example, 1, I will make a prediction for the year 2024. If I change it by 2, I add another step and the prediction would be made for 2027. I set 3, prediction would be made for 2013, 30, etc. For now, I need to make 1 step in my prediction, so I set 1. So this is the basic setup. Yes, let's run the simulation. I press the start button. We will discuss this block a little bit later. While it is being calculated, let's discuss this block. We can set separate special variable versions for simulation. By default, special variables are static, constant for both training and predicting periods. Using this function, we can say road proximity is different from the period of simulation. For example, we know that new road would be built, or, for example, new touristic points would be placed, or new buildings would be placed, or some buildings would be destroyed. So if we have dynamic data on our inputs, special variables, using this block, we can use this information and improve the process. This is extremely useful, for example, for cases where you use climate variables as predictors. Temperatures, precipitation amount, humidity, pressure, winds, etc. Because using this block, you would be able to try different scenarios. For example, use different climate models with different predictions to test, to take this information into account for land use predictions. We will use this interface a little bit later. It's one of the things we delivered in version 5, and it expands research horizons very much. So it's important thing. Okay, our simulation is finished, and let me show you all the outputs we got. For what I have done. What I have done is I closed my Mollusc. Occasionally, okay, not a big deal. Okay, let's explore what we got from the simulation. First thing is predicted land cover map. The main thing for us. This raster simulated 2024 INN1. What can I do is to explore it and compare it to our land cover maps. So we got 2018, 2021, and simulated 2024. Let's compare it with previous state. We can see the quite massive change. Model simulated that the water loss and tree cover loss continue. We can see forest loss here and water loss all around the lake, especially where settlement is located. Certainty raster is a very helpful thing. For each raster, for each pixel, it describes if model is confident or not about the transition. For example, here, I will click. I need a certainty raster. Here, in this pixel, the model is fully confident, 99%. And here, for example, we have only a few percent of confidence. Such raster could be very, very helpful in making your experiment better. You can research these areas where a model is very unconfident change your special variables, find some missing environmental factors. Like you can, as long as we can see that model is very unconfident, something is wrong for these places. Yes, and we are interested in like redesign our experiment or something like that. Sometimes if model is mostly confident, we can just ignore this information. It's on you as a researcher. And we also have the new folder named transitions with 24 rasters. We have a separate raster for each class pair. You can see by name potential from 1 to 2, from 1 to 7, from 7 to 5, etc. So we have all transition potentials here. Let me take a transition potential map for case 2. 2 is tree cover, 2, 11. Here it is, and 11 is rangeland or grassland. I added to QGIS. And here I can see how our model solved this transition. And it could be very helpful to understand the general picture, where such transitions are more probable and where less probable, how the probabilities are distributed. So for example, in this pixel, model calculated 13% probability of such transition. And in this pixel, 97% transition. So obviously in this pixel, model forced this transition, and in this pixel, I think that it was afraid of applying this transition and keep things unchanged. Okay, so it's another tool for you as a scientist to explore these potential maps, to research them, to understand how your model sees the whole process, the whole situation on your land cover dynamic. So that's it with the basic workflow. The last step is dedicated to validation. Unfortunately, I closed molluscs, but I can fastly rebuild everything because we saved the model. Proximity, slow preparatory proximity. Like that. I should recalculate changes map because it's crucial part for a model to be trained. So I create another copy of it. I'm sorry for that. On transition potential modeling, I simply load our model from file. And here I will resimulate our land cover because I need to have it simulated in this tab to use validation interface. So I just press start and wait for it to be done. Meanwhile, we can, maybe I can answer some questions from the chat because we have some. Так. Can we create many other classes based on my research objectives? So you are not limited. Gantry asked if we can create many other classes based on your research objectives. You are not limited. Mollusc doesn't limit you with classes you can use. So it also only depends on your data. So if you have land cover data sets with 100 classes, different nature, you can use this data. The main thing here is that your both initial and final rasters should have the same number of classes. So you can take, for example, Esri land cover as initial land cover dataset and MODIS dataset as final land cover dataset because they have different classes. It's impossible for Mollusc to figure out how to connect them. Yes, that's why You're not limited on the one hand, but on the other hand, you should use consistent information. Anand Kumar Gupta asked, the unit of the transition matrix is percentage or square kilometers is percentage. So the share of the whole pixels turned to this class or to this class. So we have the share percentage. No more simple questions, I believe. What is the optimum number of sample for the model training? It's impossible to say because it highly depends on your data set. It should be connected with the size of your rasters. So if, for example, if you have small 100 by 100 pixels data sets, you have small experiment, or you have very large pixels, you don't need to have thousands of samples. Yes, but if you have 5,000 by 4,000 big rasters and with different processes, you may want to have tens of thousands of samples just to, or hundreds of thousands of samples to cover the cases presented on your data. I'll return back to questions a little bit later because I got my simulation done again. I switch to validation tab and let's play a little bit with it. The only thing I have to do here is to select reference map. Simulated map has been placed here automatically after I trained it. And as a reference map, I should use, like I have actual data for 2024. So I have reference data and I can select. I push start validation. It will also take some time because it go to each pixel and compare this pixel value with reference and calculates statistics and stuff like that. So we should wait a little bit. Shortly, we'll get classic multiple resolution budget plot, and we'll get basic metrics describing the overall accuracy. Another 10 seconds and we'll continue. Maybe I should have chosen not so big case, but at least it's realistic and based on real data. Okay, it's almost done. Yep, we got multiple resolution budget plot. It's classic statistical way to reflect the quality under different like hypotheses. And if I press calculate kappa button, I get the general percent of correctness and overall kappa and kappa like histogram and location based kappas also connected with multiple resolution budget plot. It's quite like on the one hand, it's quite simple thing, but if you're interested in like understanding multiple resolution budget plots, it's better to read some papers about it before. The one like general common thing you have to look at here is this percent of correctness, reflecting the general picture. Yeah, so if it's more than 80%, you can probably use such model. The problem with validation is that usually we don't have any reference maps to validate our data. Yes, in this case, I artificially took like 2018 and 21 data as inputs, because I knew that I have 2024 raster map as a reference. But usually you have only two maps you created with blood and suffering, and you don't have anything to validate your data yet. But if you have, this interface could be quite helpful for you, and just create some general picture, general understanding of if your model is acceptable or not. Okay. What I want to do next? Oh, I can also show you one important interesting thing. I can also create a validation map by pressing this create button. I can select name for a new raster, validation, and explore it in QGIS. So I will hide all other layers and enable this layer. This raster for each pixel shows the difference between simulated state and reference state. So pixels where everything is correct are transparent. You can see it by legend, and we can see it by the map. Pixels where everything is other pixels are shown with colors, and we have a legend here. I can repeat the trick with attribute tables here, as I did with changes raster. And now we can explore it with identification tool. For example, let me ask this map what has gone wrong in this pixel. Yes, so the first value is real, presented at the reference map, and second is predicted value, so what our model predicted. So this raster shows us that in this particular picture, pixel, model predicted rangeland, but actually it should be water. And we can explore all our other pixels in the same way. What I want to do next is to repeat the simulation, but using modified special variables to show you how to work with this block. So it separates special variables version for simulation. I will close the mollusk. I think so I will close the mollusk. And my hypothetical situation would be that touristic infrastructure developed a lot in our area. So I want to simulate our land cover dynamics in the case if we will have much more points in tourism layer. So I create a copy of this layer. Was tourism extended, and create new points. I will use this as a reference. I will place a lot of new points anywhere, everywhere, just to highlight the effect we can achieve here. I think that's enough. Now let's transform this new layer to proximity map to be used as a special variable in Mollusk. So I simply run prepare vector dataset for Mollusk, select this new tourism extended layer, select proximity mode, select Esri 2018 prepared as a reference raster, and create a new raster named tourism's proximity. How to say, updated. Run the process. I got a new raster layer. It's very interesting. Looks very interesting. And now I want to rebuild the whole mollusk process, but using this raster on the last stage. So I set the same inputs. Buildings proximity, roads proximity, tourism proximity, slow prepare tourism proximity. Repeat everything I did. Update tables, create new changes map. Load the trained model from file. And select new, and here, select new simulation result raster. Let me call it simulated 2024 and then one updated tourism. Activate the set separate special variables version for simulation checkbox. And now I have to collect the same variables as an input tab, but instead of tourism proximity, I should select changed tourism proximity. So I should recreate them in the same order. So first is building proximity. Then roads proximity and slope prepared. Roads proximity, slopes prepared. But instead of taking this tourism proximity dataset, I take updated one. Then I push check consistency button. It controls if we have the same number of special variables, because we can't run the simulation with different number of special variables than we used here to train the model. And finally, I push the start button. So another prediction is in progress. And again, thanks to that function, I can test different scenarios. For example, what if we build new road here or here or here, or what if we will destroy these houses, or what if we can propose any scenarios we know, for example, from planning documents, or we can just build hypotheses and simulate land covers under different scenarios, just to show, for example, to citizens that if we will build another road here, we will lose these forests and stuff like that. And again, if you use climate variables as predictors, you can run different simulations using different climate forecasts under different climate models, etc. It could be extremely useful for land cover dynamic studies driven by climate variables. In cases like this one, of course, climate cannot be used because it's local, small territory. It would be, I guess, 1 pixel of some ERA 5 dataset. So no point in trying to use climate data here, I guess. But for some studies, why not? It fully depends on you as a researcher again. So let's wait a little bit. It took longer than I expected, but I hope you'll forget me for that. I want to show you that the result, it should be different because we changed one of the environmental factors for prediction period. Here we are. We got another simulated map, and let me compare it to the previous one. As we can see, our simulations are now different. I placed a lot of touristic points in the forest, so model predicted some advanced forest loss here and here. So yeah, this mechanism affects the simulation like very much. Okay, that's it with the workflow demonstration. To finalize our webinar, I would like to shortly discuss major limitations of Mollusc and common problems people face. The main conceptual limitation is simple, is that Mollusc is a statistical tool. Mollusc doesn't know the nature of water, nature of vegetation. It cannot reason as geographer. It just sees complex patterns in numbers and continues them into the future. So you should always keep that in mind. On the example of our case, there is no point of like having this alone pixel of water here. And as a geographer, I can say that it's crazy. A lot of small water pounds, or what is it? But mollusk don't reason doesn't reason like that. He reason only in terms of statistics, and statistics model we trained works like that. So we got what we got. You should always keep that in mind. Second thing, events out of the pattern, out of the training data, would not be predicted. For example, we observed a massive forest loss in the Blidinia National Park in Bosnia, not far away from Ramsko Jezero. But it was a forest fire. I found a piece of news like regarding this case, and I can see photo of this forest fire, etc. And nothing regarding forest fires is presented in historical datasets. So there is no way Mollusc would predict a forest fire if forest fires are not common in the location and not reflected in training data. So if some new driving factor appears after you train the model, there is no way Mollusc as a statistical tool can take it into account. The same for engineering constructions. For example, people decided to build something big and change the whole land use patterns. And statistics can't predict such things. Yes, if someone will decide to build a dam in 20 years, there is no way we can predict it based on historical data. It's very important to keep that in mind. There are several technical limitations. First one is that all data is uploaded to RAM of your computer during Mollusc workflow. So you are limited with your random access memory amount. Mollusc is effective for millions of pixels per input dataset, but not for billions. And you can simply like sum up the size of input rasters, multiply it by 2 or 3, and it would be a number Mollusc would need to process your case. It's very important on small computers with 2 or 4 gigabytes of RAM. It could be very tricky to use Mollusc with big data sets. Another limitation is that in both input land use and cover datasets should be presented the same set of classes. So if you have this set of unique values in the initial map and this set of unique values in the final map, you can't use them. It's not a big problem. There is a simple workarounds. For example, you can manually add single pixels with a serval tool in QGIS. It won't affect the simulation because single pixel won't make any difference. But yes, you should be forced to manually adjust your rasters to avoid this situation. Not very nice thing, but we got what we got. We have used a save load mechanism during our demonstration, and it is important to know that models use information about extent and dimensions of input data, and models could not be applied to datasets with different domains. So the save load mechanism currently is for multi-iteration predictions allowing the use of the same model with different versions of environmental factors, but not for applying the same model for different territories. Unfortunately, you can take my model I trained during this workshop. If I sent you via email, for example, you won't be able to like use it with your own data for different territory, because this model it's connected to the particular special domain of the data. It's important thing to consider. And the last topic for today, common mistakes people have with the mollusk. The most popular problem I see is when people try to use mollusk for cases when they have too little change over too much territory. Imagine you have large land cover maps, for example, 5,000 by 5,000 pixels. And I zoom in the first map and the same place for the second map. Having 5 million pixels in the whole land cover map, 25 million pixels in the whole land cover map, we have only a couple hundred pixels where something changed. So it's like 0.00001% of pixels have any change. From statistical point of view, it's much safer for the model to predict no change at all. So it does. So if you face that your simulated map is similar as an initial map, the reason is that you have too little change on too large territory and you use too little number of sample points to describe the transition. Imagine we place 1,000 of random points over these maps and take the information about transition. There is a 99% probability that all these 1,000 sample points would have no change pattern inside, because they would be placed in the location with no change. So model looks at this pixels, sees no change at all anywhere, and of course what it does, it proposes no change in the predictions. That's the very, very popular case. And it's better to make some small subsets of your territory where actual changes occur and work with that, not with like super big rasters without any visible change. Modeling success heavily depends on the hypothesis you propose. When selecting special variables explaining the change, yes, we used buildings proximity, roads proximity, touristic points proximity, and slope, elevation slope as predictors today. And people often use some standard sets of prediction, the same infrastructure proximities, NDVI, index values, slope, etc., as we did today. But real factors in particular case could be very different, including exotic ones, for example, beavers activity or tree parasites or anything else like that. And it's your task as a researcher to find out the real drivers and to put them into Mollusk to model, to calculate statistics and to train the model. There is no magic, unfortunately. Also, there could be different patterns and factors in different subregions of your territory. And single model could fail predicting change in areas with different nature of transformation. For example, we have very, very large territory in Australia. It's like thousands of square kilometers. And in this area, the main driver is droughts and climate change. And in this area, the main drivers are erosion and forest clear cuts. It's better to split a region into several subregions, run different experiments, use different special variables, and train different models. So don't try to build a single model trying to explain super huge territories with different genesis of processes. Yes, mollusk model is like not differentiated by territory. It's the single model. Sometimes patterns change over time. And for example, our case, Ramsco Lake, was tricky regarding the main thing, the lake body shape. Each year, the water level differs significantly. So actually, it is regulated water body, and it depends on many factors besides environmental, what level of water we observe. We have a dam here, we have maybe some hydro electro facilities somewhere connected with this lake. So it could be quite tricky thing to predict the change for such water bodies because this change depends not only of environmental factors, but also decisions people make, government make, etc. And MOLUSCE, if MOLUSCE observes this pattern on the training period, it will just apply it to the future because it's just statistics again. I believe that's it from my side. Thank you very much for your attention. Explore our technologies at nextgis.com. Join discussions at our community forum, community.nextgis.com. Contact us via email, follow us on LinkedIn, enroll in our university support program. And if you want to discuss anything, we do have time now. Please, I'm a little bit tired, but